Nir Sever brings us over 30 years of technological and managerial experience in advanced VLSI engineering. Before joining Proteantecs, Nir served for 10 years as the COO of Tahuti Networks, a pioneer in high-speed networking and semiconductors. So thank you, Nir.
And thank you very much, Ira and Neil, for the introduction. And today I'm going to talk about lifetime performance and health monitoring of high bandwidth die-to-die interface using chip telemetry. And because I am coming from a rather small company, I think it'll take a minute or two just to introduce to you of who Proteantecs is. So we are a startup company that was founded about 4 years ago by industry veterans, people who also founded Mellanox Technologies. That was one of the most successful technological company in Israel before being acquired by NVIDIA. So we all are coming from deep VLSI product background. We are headquarters in Israel with global reach, and today covering North America as well as Europe and Asia. We are shipping already products in advanced FinFET technologies from 28 nanometer and below. And we have key customers in market segments such as data center, automotive, and communication. The reason that this company was founded was because the founders realized that there is a gap in the industry for a comprehensive solution for taking a design and walking it through its entire lifetime from design through manufacturing. And with advanced process technologies, with advanced use case requiring 24/7 availability, we are seeing actually that we believe that the industry is not yet prepared for that scale because it is very siloed. The outcome are observation about chips that taking 12 to 8 months to debug and bring to production, warranty claims that are increasing and hurting the bottom line of companies. Many of the RMAs and the bug reports are coming as investigation inconclusive, and we are seeing real failures of advanced electronics, for example, in cars, that is very worrisome. So with scaling, I guess this audience already understands the importance of heterogeneous integration or advanced packaging or system in package, whatever name you give it. The fact is that advanced electronics today must scale beyond just CMOS scaling, and it is doing so by adopting advanced packaging and interconnect technologies to overcome different hurdles such as reticle limitation, to be able to do heterogeneous integration of silicon components that were manufactured in different processes, and to increase the economical worth of products with the concept of chiplets. So instead of designing one chip for each product, you can actually design like a library of chiplets and mix and match to create a wealth of product out of the same already verified silicon. And with this advanced technology comes many challenges. And usually I would like to look at the challenges of advanced packaging in 2 dimensions. One dimension is the packaging or substrate technology, and the other dimension is the interconnect itself. The interconnect is probably the most important thing to make this product viable. In terms of substrate technologies, the 2 main technologies are silicon interposers and organic substrates. They have different names by different vendors. For example, TSMC call their silicon interposer CoWoS, and the organic substrate is Info. Different terminologies used by Intel. And in terms of the interconnect technologies, again, you can roughly divide it into 2. Serial interconnect based on the high-speed SerDeSes. So these are very high-speed high-speed data rates on fewer data lanes, while the other one is parallel, in which you actually take advantage of the fact that you have a lot of interconnect capacity on a substrate, and therefore you can put many more parallel connections, each one becoming or being more simpler and running at lower data rates. But the fact is that there are shared problems and challenges, and these are the challenges that we are going to address in the next of this presentation. And specifically for those parallel interfaces, we're talking about thousands and sometimes over 10 of thousands of interconnect lanes between two adjacent dies on this package. And each one of those can be actually a single point of failure. Depending on the packaging technology itself, the failure are mostly associated with the micro bumps or with the lane traces on the substrate or the through silicon vias. Each one can have a failure, either catastrophic failure or a defect that will cause it to misbehave. And not only some of those defects are happening during packaging, considering the amount of stress and heat that these packages are suffering during manufacturing, even latent defects that may not be visible at day one may degrade over time. And we are hearing reports about the degradation of micro bumps and lanes. And over time, defects that may not be observed can become actually catastrophic failure and causing a lane or more lanes to actually completely fail. Another challenge is the lack of visibility. So unlike a discrete component where you can probe the pins of the chip, once you cover the substrate with the dies, you are losing any probing capability. So you can no longer probe the traces because they are completely obscured by the dies and by the packaging substrate, and there is no really good technology to look and touch a single wire and look at the signal going over it. And moreover is that there is no common way to continue and observe the quality of those interconnects while the chip is fully deployed and in complete mission operation mode. So what Proteantecs bring to the table is what we call visibility at every stage. So we've built a visibility system. I'm not going to touch about all that we do because I'm going to focus only on this heterogeneous integration solution, but think about eyes that are implanted in your design during the chip design itself, allowing you to get visibility through the chip production and system production and all the way to in-field, in order to allow you for a faster time to market, higher quality, reduce your failure cost, and prevent failures in the field. The solution is based on two main concepts. One is what we call deep data through in-chip telemetry. So these are small circuits, we call them agents, that are implanted into the chip and provide different type of parametric measurement that can be then extracted out of the chip. And the other aspect is our data analytics platform that is cloud-based, that is running machine learning and other dedicated algorithms to process the data and provides alerts and actionable insights using that data. The data can be from one chip or from the entire fleet of chips deployed in the field. So the Universal Chip Telemetry are those agents that I mentioned. What they are actually very small circuits. Most of them are completely digital or high-speed circuits. They are designed to do a parametric measurement, and they are designed for analytics. Because they are very small, they can be spread in high coverage and with high resolution, and only causing a minimal or negligible power, performance, and area penalty. They are designed to operate in test mode as well as in mission mode. to address the different use cases that I'm going to mention. And they are used to sense the electronics inside the chip as well as the surrounding electronics of the environment in which this chip is working. And we're offering different classes of agents, but today we are only going to talk about our interconnect performance and degradation monitoring. And if you have more interest, then feel free to contact us and you'll find much more information about our complete visibility platform. Our technology, as I said before, is silicon proven. It's already been deployed in customer products from 28 nanometer and down to 5 nanometer, and moving forward even to more advanced nodes. Before I continue into going to the details of our solution, are there any questions so far?
Yes, Nir, there was one question back, I think, on the visibility aspect. Jan is asking, what if we do X-ray inspection to look for void in the solder joints or other defects?
Yeah. So first of all, from what I understand, X-ray is complicated because the dye itself and the substrate is obscuring and interrupting X-ray technology. Not everything can be visible by X-ray, but even more than that, think about the fact that you have to know that you have a problem in order to X-ray it. You think about 10 of thousands of micro bumps, 10 to 20 micron pitch, and you have to look into each and every one of them to understand if there is just a minor void or crack. And if you're going to X-ray every single component, you're going to waste a lot of time, even if you had the way to do that. So X-ray is a good debug aid, we believe, but in order to really get to the bottom of or sort out a problem, we believe that visibility from within is the better way. Okay.
Thank you.
Okay. So to address this type of a product of high-speed parallel interconnect, we've developed our UCT agent that is called the tile connectivity agent. It is basically, again, a small circuit that is embedded inside the PHY, inside the die-to-die parallel PHY. It is designed to be general purpose. So it was already implemented in different substrate technologies such as INFO and CoWoS, and there is no reason why it cannot be implemented into other substrate technologies. And it is indifferent to the protocol running over the interface. So whether it's AIB, HBM2, HBM3, OpenHBI, BOW, proprietary algorithms such as protocols such as Glink or AP-Link, all that can be supported by the same type of agent. The concept we are using is ongoing tracking of the signal at the receiver, and basically measuring what we call margin to fail. Basically, it's the difference between two different reference signals or one signal and maybe a reference clock. And it's designed to be working in mission mode. So without interrupting the signal, this agent is more continuously monitoring the quality of the signal and looking into the margins of that signal. It is designed to support a wide speed range from 2 gigahertz or 4 gigabit per second and all the way up to 8 gigahertz or 16 gigabit per second. And out of the measurements, we can recreate under our software platform a full eye visibility for a double data rate signals by measuring setup and hold positive and negative edges of the reference clock or a reference signal. And this agent is a one for addressing all type of signals. So that could be a receive only, transmit only, bidirectional, single-ended or differential. And we can do this monitoring from one side of the link. Typically that would be the case in an HBM, or from both sides of the link if this is more like a symmetrical parallel interface such as a G-Link or a AAD. Not only we provide this agent, we also provide a complete system level solution. So we provide the hierarchy of controllers. Controllers are designed in or provided as a synthesizable RDL form, or maybe I didn't mention, but the sensor itself or this agent itself is provided as a circuit, as a hard IP circuit, already targeting to the target process technology of the intended device. The controllers are synthesizable RTL, and they are designed for integration into a PHY digital layer such as PCS, or even at a higher level of the hierarchy. A number of I/O sensors, those are those small circuits, are connected to a single block controller. The block controller is responsible for configuring the sensors, sending them commands and extracting data, and doing the first level of data processing, what we call the edge processing, already inside the controller. The purpose is to reduce the amount of data that will be then extracted outside of the chip. And then a number of block controllers will be connected to the top controller. The top controller is responsible for the data storage, so it has its own FIFOs, as well as the connection to the upper layer of the system. And if this chip is still on an ATE, typically it will be connected outside to the world using debug ports such as a JTAG or I2C. And if it's already deployed in mission, then it will be connected to an onboard CPU, such as a microcontroller, probably using an APB port.
Hey Nir, we had another question. Can the D2D agent tell if the issue is in the trace or the microbump or the BEOL or FEOL circuitry?
That's an excellent question, and spare with me for a moment, because when I'm going to talk about the use cases, I'm going to talk about that.
Got it. Thank you.
Thank you. So I said that only half of our solution is this circuit. The other one is the Proteus platform itself, which again, it's a deep data analytics platform that is already coming to you out of the box, equipped with specific dashboards. It is cloud-based, but it can also be hosted on-prem. It is capable of machine learning, coming with already algorithms loaded, as well as open to implement your own algorithms and dashboards. And it is open to integration with data coming from other sources, not just our own agents. These are just some of the examples of the dashboard, our general purpose dashboards that are coming with the Proteus platform. And another nice thing about it is that we have developed what we call a common language. So regardless of where the chip is in its life cycle, the same type of data in the same type of data format is used. So one language is adopted across the entire lifetime of the chip, whether it's still in the designer hand, in the manufacturing facility, or already deployed in the field. Same type of data will be extracted and then uploaded for analytics in our analytics platform. So I will now go and describe some of the typical use cases of this system, and then now is the time to answer your question. So typically, when you are looking into testing an interconnect, and especially a high bandwidth, high width interconnect, mostly the most common way to do it is through a BEAST. This is a way to put the chip into a specific test mode, run some data, and test that using a loopback that the data is indeed received correctly or not. Typically, this will give you a pass-fail indication, so you know if a lane is good or not. And that's why I'm painting this world in black and white. And again, exactly to your question, I'm painting the entire lane in black and white, because when you have a failure, you don't know what's the source of the failure. These systems doesn't give you the answer. We, however, are doing a full lane grading. Lane grading meaning that we are getting you parametric reading. So not just 0 or 1, we're actually giving you a number, or actually a set of numbers for each lane that represents the quality of the signal. And because we have different measuring modes, we can actually pinpoint the location of a failure or actually a defect to where it is most probably. We cannot say it for 100%, but by crossing measurements from different sides of the link, we can pinpoint the problem to be a degradation of the receiver, the transmitter, a microbump, a near-end microbump, or a far-end microbump, or the lane in between, and all that by correlating and crossing different measurements that were collected during the operation, during the data transfer over the lane. So I hope this answers this question. Where this is typically used, first of all, during NPI. So you get your first batch of chips and you want to test and characterize the interfaces. So again, compared to a go, no go that you'll typically get using your BEAST running over a loopback test. In our case, you'll get full parametric measurement that allow you to get and see full visibility per pin. So I want to emphasize our circuitry is designed to be placed on 100% of the pins. All the pins are covered, not just sample off. So you'll get full eye visibility on 100% of the pins, and you get the analytics to understand what's going on. This is an example used by one of our partners, GUC, in which they actually use that capability to characterize their substrate. So they've designed an HBM PHY, and they wanted to understand what's the robustness of the PHY. So they actually created the test chip in which they routed the substrate lanes in different manners. Some are very short and straight, and some are actually distant and zigzagged. And using this technology, they were able to understand exactly what's the limitation of the technology. And of course, obviously blue means that the signal quality is very good, and red is marginal or not good. And again, that was done intentionally to understand the limitation of the PHY technology they've used. During high volume manufacturing, your attention is to identify outliers. Outlier can be a single pin out of those 10 of thousands of lanes. It is very important to know that most of those parallel interfaces employ spur lanes. However, in order to use a spur lane, you have to understand which pin is defected, and then you have to configure the spur lane to be activated. So we allow you by using our outlier detection mechanism to understand which are the weakest points already during manufacturing, and giving you an alert that you can use to switch to a spur lanes this pin. Of course, if you have multiple pins or you see growing number of pins failing in your manufacturing line, then this may indicate some sort of pandemic, and you may want to stop your manufacturing line and take some preventive action. This is again an example of how we are showing these statistics. Again, GUC used that capability to understand if the substrate that they've assembled had outlier pins, and indeed in this case, they could identify a couple of pins that had measurements that were unexpected or outside the manufacturing process limits. Most importantly, this system is continuing to be used during full operation of the chip. So the chip is already deployed in the system. It is running real data, and we keep collecting and processing this information. Once in a while, you as a system operator will upload the data into our data analytics platform, and you will get information and allowing you to produce alerts. So you can actually program a degradation alert, which is a threshold that tells you, okay, if any of the signals falls below a certain limit, send me an alert, and then I will put the system into maintenance mode. I will switch to the spur lane and continue the mission uninterrupted. The idea of this, what we call predictive maintenance, is to never make a system fail in the field by actually detecting those faults before they becoming a real failure. This is again, to summarize, an example of dies embedded or assembled over a substrate. You can see on the left-hand side a small resistive short that was created between two adjacent wires that caused a signal to be slow to rise and slow to fall and not even reach rail. and our data analytics platform was able to identify that this is an outlier compared to the group of similar pins on the same interface, and therefore giving you an indication that this is a good candidate for a spur lane. Degradation over the field, unfortunately, I'm not allowed to show you a real case, although we did run stress testing by a customer, and they were able to really see how latent defects are becoming more and more severe until they become a failure. But in this test, we actually manually modified the resistance, the drive strength of the receiver and the sensitivity of the receiver and the drive strength of the transmitter. And our agent was able to catch those small variances and detect something that could indicate a real degradation of the buffer or an increase of the resistance of a micro bump or a lane. So to summarize, we offer a complete solution for lifecycle visibility into the high-speed, high-bandwidth interconnect of data interfaces that can be used during NPI for an accurate per-pin characterization, for high-confidence production testing during mass production, and to assure for uninterrupted service availability when the system is deployed in the field. So thank you very much, and I will be happy to take remaining questions.
Yes, we have a few questions in the chat. Can you speak to the area trade-off with the agent? And is there a general power performance to area cost for putting these agents on the design?
Thank you. So I would say that the area of this circuit, of the hard IP circuit, is in the range of 10 microns square. If you think about a pitch of a few tens of microns apart, it means that the area budget allocated for each transceiver in these high-speed interfaces is more than enough to accommodate for that sensor. Again, when I'm talking about 10 square micron, that's about 3/3, not 10/10. So it's very, very small compared to the pitch. The power is negligible. It is fully digital, and it is running at relatively low, except for a small circuit that, of course, is high-speed measurement. We immediately reduce the amount of data and the clock rate. So it is not consuming significant power compared again to the transceiver itself. And the logic itself is just a few thousand of gates, which is meaningless in the context of a full chip.
Dave was asking, is that size per lane?
That's a size per lane, exactly. So this few microns square is per lane. And again, think about the area allocated for one lane. It's very, very small compared to the entire circuit area. So none of our customers so far had any problem to find room to place this small IO sensor.
Okay. Can you talk to your relationship with GUC, and does GUC by default include this monitor into their Glink IP?
That's correct. So we've been developing this technology actually first with GUC. GUC are not our only customer, but we definitely need to give them the credit for helping us bring it up. And our technology is embedded into both their HBM, so all their HBM PHYs, the modern ones, from 7 nanometer and below, and their Glink PHYs are including our technology embedded. And of course, in order to connect that, you'll need to talk to us, and you'll get all the information about how to connect that and how to deploy the data analytics in your environment.
Okay, and I think on one of your use cases, you were talking about finding outliers and groups of lanes. Can you speak to how big those groups were and how did you define those groups?
So for example, it really depends on the protocol, but for example, in an HBM, a typical what's called the 32DQ is comprised of 32 bidirectional pins and associated clocks and strobe signals. So that usually is called a pin group. And each pin group typically have one spur lane. So you have to identify which group is failing, which pin in the group is failing to be able to activate that spare length for that group. But it really depends on the protocol. Different protocols may have different, what we call group definition. But the comparison we are doing is, first of all, we want to understand the pin relationship to the group because that's the reference. But we also compare the same pin to all the pins to the same pin in all the other chips. So we can do many type of data analytics to understand which pins are actually misbehaving versus what's the normal range of behavior for that pin.
Okay, and I think we have time for one more. There's a question on how does this work with chiplets, and especially in cases when not all the chips may have agents on them, and is there a need for a data connection between the chiplets to kind of manage those analytics?
Yeah, thank you. So as I mentioned before, we prefer that you'll use our agents, of course, in all your chiplets, and meaning both sides of the link. However, it was designed to also be placed on only one side of the link. And again, HBM is the best example. In HBM, we are not assuming that we are on the memory side, but only on the SoC side. And there is no requirement to have our own data links between the chips. The DUT is where our agents are placed, and it is from where the data is extracted, and we don't care about the other side. Of course, if you do have the agent on the other side, then we cross the data already in the platform. Then we know which data is coming from which die on the chiplet, and we know, say, okay, these two data sets or data streams are actually connected to the same product, and therefore we can create more analytics related to that.
Okay, thank you.
I'd like to thank all the presenters and also thank all the sponsors who made this event possible, and their generosity covered the expenses, so everybody was able to attend without charge. Our diamond sponsor is Amcor with differentiations in technology, quality, and service. Our emerald sponsors are Advantest, voted #1 in ATE by the VLSI survey in 2001, and Synopsys, silicon to software. And then our Ruby sponsor, Tech Search International. So once again, if you have an opportunity to thank the sponsors, please do so to encourage them to help support future events and bring great information like we've had over the last 3 days here at Data and Test Road to Chiplets. And with that, I will wish everybody a good rest of your day. And thank you for joining us, and look forward to seeing you at a future MEPTech event. Thank you.